Random access memory is a form of computer data storage. A random access memory device allows data items to be accessed in almost the same amount of time irrespective of the physical location of data inside the memory. In contrast with other direct-access data storage media such as hard disks, CD-RWs, DVD-RWs and the older drum memory, the time required to read and write data items varies significantly depending on their physical locations on the recording medium, due to mechanical limitations such as media rotation speeds and arm movement. Today, random access memory takes the form of integrated circuits. RAM is normally associated with volatile types of memory, where stored information is lost if power is removed. Although many efforts have been made to develop non-volatile RAM chips, other types of non-volatile memory exist that allow random access for read operations, but either do not allow write operations or have limitations on them. These include most types of ROM and a type of flash memory called NOR flash. Integrated circuit RAM chips came into the market in the late 1960s, with the first commercially available DRAM chip, the Intel 1103, introduced in October 1970. History. Early computers used relays, mechanical counters or delay lines for main memory functions. Ultrasonic delay lines could only reproduce data in the order it was written. Drum memory could be expanded at relatively low cost, but efficient retrieval of memory items required knowledge of the physical layout of the drum to optimize speed. Latches built out of vacuum tube triodes, and later, out of discrete transistors, were used for smaller and faster memories such as registers. Such registers were relatively large and too costly to use for large amounts of data. Generally only a few dozen or few hundred bits of such memory could be provided. The first practical form of random access memory was the Williams tube starting in 1947. It stored data as electrically charged spots on the face of a cathode ray tube. Since the electron beam of the court could read and write the spots on the tube in any order, memory was random access. The capacity of the Williams tube was a few hundred to around 1,000 bits, but it was much smaller, faster, and more power efficient than using individual vacuum tube latches. Developed at the University of Manchester in England, the Williams tube provided the medium on which the first electronically stored memory program was implemented in the Manchester small-scale experimental machine computer, which first successfully ran a program on the 21st of June 1948. In fact, rather than the Williams tube memory being designed for the SSEM was a testbed to demonstrate the reliability of the memory. Magnetic core memory was invented in 1947 and developed up until the mid-1970s. It became a widespread form of random access memory, relying on an array of magnetized rings. By changing the sense of each ring's magnetization, data could be stored with one bit stored per ring. Since every ring had a combination of address wires to select and read or write it, access to any memory location in any sequence was possible. Magnetic core memory was the standard form of memory system until displaced by solid-state memory in integrated circuits. Starting in the early 1970s, Robert H. Dennard invented dynamic random access memory in 1968. This allowed replacement of a 4 or 6 transistor latch circuit by a single transistor for each memory bit, greatly increasing memory density at the cost of volatility. Data was stored in the tiny capacitance of each transistor, and had to be periodically refreshed every few milliseconds before the charge could leak away. Prior to the development of integrated read-only memory circuits, permanent random access memory was often constructed using diode matrices driven by address decoders, or specially wound core rope memory planes. Types of RAM. The two main forms of modern RAM are static RAM and dynamic RAM. In SRAM, a bit of data is stored using the state of a 6-transistor memory cell. This form of RAM is more expensive to produce but is generally faster and requires less power than DRAM in modern computers. Is often used as cache memory for the CPU. DRAM stores a bit of data using a transistor and capacitor pair, which together comprise the DRAM memory cell. The capacitor holds a high or low charge, and the transistor acts as a switch that lets the control circuitry on the chip read the capacitor's data charge or change it. As this form of memory is less expensive to produce than static RAM, it is the predominant form of computer memory used in modern computers. Both static and dynamic RAM are considered volatile, as their state is lost or reset when power is removed from the system. By contrast, read-only memory stores data by permanently enabling or disabling selected transistors, such that the memory cannot be altered. Writable variants of ROM share properties of both ROM and RAM, enabling data to persist without power and to be updated without requiring special equipment. These persistent forms of semiconductor ROM include USB flash drives, memory cards for cameras and portable devices, etc. ECC memory includes special circuitry to detect or correct random faults in the stored data, using parity bits or error correction code. In general, the term RAM refers solely to solid-state memory devices, and more specifically the main memory in most computers. In optical storage, the term DVD-RAM is somewhat of a misnomer since, unlike CD-RW or DVD-RW, it does not need to be erased before reuse. Nevertheless, a DVD-RAM behaves much like a hard disk drive if somewhat slower. Memory hierarchy. One can read and overwrite data in RAM. Many computer systems have a memory hierarchy consisting of processor registers, on-die SRAM caches, external caches, DRAM, paging systems and virtual memory or swap space on a hard drive. This entire pool of memory may be referred to as RAM by many developers, even though the various subsystems can have very different access times, violating the original concept behind the random access term in RAM. Even within a hierarchy level such as DRAM, the specific row, column, bank, rank, channel, or interleave organization of the components make the access time variable, although not to the extent that rotating storage media or a tape is variable. The overall goal of using a memory hierarchy is to obtain the higher possible average access performance while minimizing the total cost of the entire memory system. In many modern personal computers, the RAM comes in an easily upgraded form of modules called memory modules or DRAM modules about the size of a few sticks of chewing gum. These can quickly be replaced should they become damaged or when changing needs demand more storage capacity. As suggested above, smaller amounts of RAM are also integrated in the CPU and other ICs on the motherboard, as well as in hard drives, CD-ROMs, and several other parts of the computer system. Other uses of RAM. In addition to serving as temporary storage and working space for the operating system and applications, RAM is used in numerous other ways. Virtual memory. Most modern operating systems employ a method of extending RAM capacity, known as virtual memory. A portion of the computer's hard drive is set aside for a paging file or a scratch partition, and the combination of physical RAM and the paging file form the system's total memory. When the system runs low on physical memory, it can swap portions of RAM to the paging file to make room for new data, as well as to read previously swapped information back into RAM. Excessive use of this mechanism results in thrashing and generally hampers overall system performance, mainly because hard drives are far slower than RAM. RAM disk software can partition a portion of a computer's RAM, allowing it to act as a much faster hard drive that is called a RAM disk. A RAM disk loses the stored data when the computer is shut down, unless memory is arranged to have a standby battery source. Shadow RAM. Sometimes, the contents of a relatively slow ROM chip are copied to read/write memory to allow for shorter access times. The ROM chip is then disabled while the initialized memory locations are switched in on the same block of addresses. This process, sometimes called shadowing, is fairly common in both computers and embedded systems. As a common example, the BIOS in typical personal computers often has an option called Use Shadow BIOS, or similar. When enabled, functions relying on data from the BIOS's ROM will instead use DRAM locations. Depending on the system, this may not result in increased performance, and may cause incompatibilities. For example, some hardware may be inaccessible to the operating system if shadow RAM is used. On some systems the benefit may be hypothetical because the BIOS is not used after booting in favor of direct hardware access. Free memory is reduced by the size of the shadowed ROMs. Recent developments. Several new types of non-volatile RAM, which will preserve data while powered down, are under development. The technologies used include carbon nanotubes and approaches utilizing tunnel magnetresistance. Amongst the first-generation MRAM, a chip was manufactured with 0.18 micrometers technology in the summer of 2003. In June 2004, Infineon Technologies unveiled a prototype again based on 0.18 micrometers technology. There are two second-generation techniques currently in development. Thermal-assisted switching, which is being developed by Crocus Technology, and spin transfer torque, on which Crocus, Hynix, IBM, and several other companies are working. Nantero built a functioning carbon nanotube memory prototype array in 2004. Whether some of these technologies will be able to eventually take a significant market share from either DRAM, SRAM, or flash memory technology, however, remains to be seen. Since 2006, solid-state drives, with capacities exceeding 256 GB and performance far exceeding traditional disks, have become available. This development has started to blur the definition between traditional random access memory and disks, dramatically reducing the difference in performance. Some kinds of random access memory, such as EcoRAM, are specifically designed for server farms, where low power consumption is more important than speed. Memory wall. The memory wall is the growing disparity of speed between CPU and memory outside the CPU chip. An important reason for this disparity is the limited communication bandwidth beyond chip boundaries. From 1986 to 2000, CPU speed improved at an annual rate of 55%, while memory speed only improved at 10%. Given these trends, it was expected that memory latency would become an overwhelming bottleneck in computer performance. CPU speed improvements slowed significantly, partly due to major physical barriers and partly because current CPU designs have already hit the memory wall in some sense. Intel summarized these causes in a 2005 document. First of all, as chip geometries shrink and clock frequencies rise, the transistor leakage current increases, leading to excess power consumption and heat. Secondly, the advantages of higher clock speeds are in part negated by memory latency, since memory access times have not been able to keep pace with increasing clock frequencies. Third, for certain applications, traditional serial architectures are becoming less efficient as processors get faster, further undercutting any gains that frequency increases might otherwise buy. In addition, partly due to limitations in the means of producing inductance within solid-state devices, resistance capacitance delays in signal transmission are growing as feature sizes shrink, imposing an additional bottleneck that frequency increases don't address. The RC delays in signal transmission were also noted in clock rate versus IPC, the end of the road for conventional microarchitectures, which projects a maximum of 12.5% average annual CPU performance improvement between 2000 and 2014. A different concept is the processor memory performance gap, which can be addressed by 3D computer chips that reduce the distance between the logic and memory aspects that are further apart in a 2D chip. Memory subsystem design requires a focus on the gap, which is widening over time. The main method of bridging the gap is the use of caches, small amounts of high-speed memory that houses recent operations and instructions nearby the processor, speeding up the execution of those operations or instructions in cases where they are called upon frequently. Multiple levels of caching have been developed in order to deal with the widening of the gap, and the performance of high-speed modern computers are reliant on evolving caching techniques. There can be up to a 53% difference between the growth in speed of processor speeds and the lagging speed of main memory access.